Welcome. We're taking a look at lesson 11.5, which is confidence intervals. But before we do that, let's review two problems over the central limit theorem. So first off, we have a problem that says the average cost of a gallon of gasoline in a U.S. city is $1.75. You can tell it's not a current problem anymore with standard deviation of 13 cents, which basically means that over 60% of values will be either 13 cents less or 13 cents more. If you look at those gallon of gasoline prices, that would have over 60% of all gas prices. So here's the mean, which we use mu, $1.75. And the standard deviation is represented by sigma, 13 cents. It's kind of the idea of how far prices are separate from one another. It says if a random sample of 25 gas stations is surveyed or selected, whoops, let me rewrite that again, 25, there we go. Find the probability that the mean of the sample will be between $1.65 and $1.80. And again, the way we wrote this is we'd say the probability is between $1.65. That means it could be equal to. Oh, well, actually, between typically does not mean equal to. I'm sorry. Let me change that. So $1.65 is less than X, which is less than $1.80. That's what we're trying to solve for there, the probability. So to do so, I'm going to go to the central limit theorem. And what we found out is the mean of the population is $1.75. The standard deviation is 13 cents. We have 25 samples, and we want to know the sample, what is the probability of the sample mean being between $1.65 and $1.80. So I'm going to first put in here the mean of the sample at $1.65 and get our standard error value. And not only that, what's more important, oftentimes would be the Z value if you're going to go off of that. So here we are looking at this value, and the Z value is now appearing is negative 3.846. So what I'm going to do with that, what we learned last time, is I'm going to come over here just so you can see the distribution. I'm going to type in the Z value in right here. So we want all prices in between the Z value 3.8461538. I'm just going to stop there. And let's find out the maximum now. We want to know the mean or the maximum mean value of $1.80. And so I'm going to come back over here and put $1.80. Standard error is still the same value, but this time the Z value would be a 1.92. That would be the maximum. So let's go type that in, 1.9230769. And we're getting pretty well that this will, we have a 97.3% chance of having a probability in between $1.65 and $1.80. So 97.3 would be the correct answer here on number one. Number two, a website conducted an online poll where it was determined that 20% of stay-at-home mothers were working part-time from home. Find the probability that out of 45 randomly selected stay-at-home mothers, at least 10 and at most 20 were working part-time. So a couple things about this is one, this must be binomial because they're saying there's like two options. You can either 20% stay at home or working part-time, I should say, which I could just say 0.2, but I'll leave it as 0.20. And there's also another value. There's a binomial, means there's two options. That means if 20% were not, that means, or were, it means 80% are not working part-time, which would be a 0.8. For the record, my wife, this would apply to her, she would be part of this 20%. Now it says find the probability that out of 45 random selected stay-at-home moms, at least 10, that means you could be equal to 10, and at most 20 were working part-time. Now, when we do a binomial approximation, there is a conversion, which we talked about last class. And what I'm going to do here is I'm going to go down to this normal approximation, type in our values. We said that n is 45 here, and I'm going to turn this one off for a moment. The probability is 0.20, and so this automatically came up with the probability of failure at 80% or 0.8. And now we have this binomial distribution. We want to look at what's the probability that at least 10 and at most 20, which we would think the answer is going to be 35 0.5, which would be A. But this is not exactly correct because there is this conversion that we need to go over. If we can be equal to the value, so not just, let me write that out here. We're looking for the probability that we have at least 10 and at most 20. Now we have a correction factor that we need to come up with for this probability. So I have it right here on the left, and just kind of remind you that binomial, we need to come up with some, so let me refresh here. Let me pause and explain this to you. What's happening here is this is the normal approximation, and it has it, what we would, if you look at this, this is a continuous curve. Continuous is the word I was looking for there, meaning there's no breaks. But binomial, the truth is you can't have like 4.5 people saying something, or 4.5 would be somewhere in the middle here, or 5.5 people, something like that. And so we need to really adjust this to make sure we involve the right amount for the probability. And so the binomial adjustment actually coincidentally involves a decimal. And so it's kind of strange, but this is the way it works. And so if you're saying 10 is less than or equal to x, if I come over here, this is it's basically the same thing, just written the other way. X is greater than or equal to that number 10. What you would need to do is subtract the 0.5. So truthfully, the probability that I would be looking at, let me write it out, one full time, it would be minus 0.5 is less than or equal to x, which is less than or equal to. And now less than or equal to the number 20 means I need to add 0.5. So 20.0.5. And so the probability here for a binomial approximation would be the probability that 9.5 is less than or equal to x, which is less than or equal to 20.5. That's actually what I need to calculate here, which will increase the amount of shaded area. And it also increases my number up to 42.6%. And so that would be my probability. We went from A to B just by increasing our probabilities, and that is the binomial distribution correction factor. That's what that was. Correction factor is what I need to say here.